aldol condensation. Now, when an aldol addition product undergoes a dehydration process, we call this as condensation. You guys already know what's the meaning for dehydration. Dehydration is removal of water. Okay. So some organic compounds, when heated, they will give off water, right? So when an aldol addition product undergoes dehydration, it generally forms the alpha beta unsaturated aldehydes and ketones. Alpha beta unsaturated aldehydes or ketones. Okay. Now, in general, beta hydroxyketones are easier to dehydrate. And the reason for that is actually going to come from the structure. The double bond formed when the compound is dehydrated is actually conjugated with the carbonyl group, and this conjugation is going to increase the stability of the product. Okay, so dehydration is again a condensation reaction. Condensation reaction is a reaction where there is a formation of new carbon-carbon single bond while removing small molecules such as water or alcohol. Okay, so condensation is actually formation of new carbon-carbon single bonds along with elimination of small molecules such as water or alcohol. Okay, now let's look into the mechanism for the aldol condensation reaction. Let's first draw the product for the reaction, and then we'll go for the mechanism. Okay, aldol condensation reaction proceeds with either two aldehydes or two ketones, where it is first converted into an aldol addition product, and then when it is heated, it's going to give the alpha beta unsaturated ketone or an aldehyde. Okay, so this is acetone, 2 moles of acetone, 2 molecules of acetone reacts with a base in the presence of water, and this is the aldol addition product that you will get from this reaction, which is a beta hydroxy ketone. Again, the name comes from the thing. Here is your keto group, and this is the alpha position. This is the alpha position, and this is the beta position, and the hydroxy group is actually on the beta carbon, and therefore it's a beta hydroxy ketone. And when you heat this in the presence of a base, water is going to get eliminated, and you will actually form a double bond between the two carbons by losing the water molecule. Okay, so let's look into the mechanism for this reaction. So let's take our beta hydroxy ketone. So here is our beta hydroxy ketone. So the base will go and abstract this hydrogen, acidic hydrogen, creating an enolate ion. And this enolate ion is going to be in resonance with the other structure. And then these electrons on the negatively charged oxygen is going to come back in, and the double bond is going to break, and it's going to shift the adjacent carbon, and the water molecule is going to accept this OH, the hydrogen from the water molecule is going to accept this OH, and the OH is going to leave. Okay, and that's going to give the product. So you can tell that this is an alpha beta unsaturated carbonyl compound, because as you can see from the structure, here is my carbonyl compound in alpha beta, and there is a double bond between alpha and the beta position, so it's called as alpha beta unsaturated carbonyl compound. One special thing to say about this mechanism is it is going to follow the E1CB mechanism. And so far we have talked about E1 mechanism and E2 mechanism, elimination, unimolecular elimination reactions and bimolecular elimination reaction. But this one is actually a special kind of mechanism, E1CB. E1CB actually stands for first order elimination conjugate base. Conjugate base elimination reaction. Here, carbanion, you can see that there is a carbanion formed. Remember, in the E1 elimination reaction, there is a carbocation formed. But in this particular elimination reaction, there is a carbanion formed. Okay, and if the carbanion is not resonance stabilized, or if it's not electron delocalized, then this reaction is not going to happen at all. So the stability of the carbanion is going to be more important. Okay, and yeah, so this is aldol condensation reaction. Okay, and again, dehydration can also happen without heat. For some carbonyl compounds, dehydration can happen without heat. So there is a driving force in the molecule. Let's see what is that driving force. Can happen without heat. Suppose if you take this particular molecule. Okay, so this is a ketone. This is acetophenone. And when you take 2 moles of this and react it with OH minus in the presence of water, it's first going to form the beta dihydroxyketone. Okay, and here is the structure for it. Remember, one of the molecule is going to act as a nucleophile, while the other is going to act as an electrophile through conjugate addition, and then the elimination happens. Elimination of water molecule. Okay, so when this compound eliminates water, it's going to form this product, which is again an alpha beta unsaturated carbonyl compound. Okay, this molecule right here, it's actually going to lose water molecule super fast, because the new bond that is actually conjugated between conjugated not only with the carbonyl group but also with the benzene ring. So let's see, so you have the new double bond right there, right? But this double bond is actually conjugated with the carbonyl double bond, the double bond in the carbonyl group, and also the double bond in the benzene molecule or the phenyl group. Okay, and that's actually going to be the driving force. The stability of this molecule is the driving force for this reaction. Okay, The last one is the crossed aldol addition reaction. Okay, so this is an aldol addition reaction where two different carbonyl compounds are used. Say, for example, in all of these cases, we have seen that two aldehydes or two ketones gave the products, right? But here in this case, in the crossed aldol reaction, we are going to write it as A plus B gives products. So where A could be an aldehyde, in the first case, A could be an aldehyde and B could be a ketone. In the second case, A could be one aldehyde, I'm going to write it as type 1, and B could be another aldehyde. Or in case 3, A could be a ketone and B could be a second ketone. Okay, so in all of these, in this particular reaction, we'll be using two different carbonyl compounds. Okay, so here is an example. So here they are reacting with two different aldehydes. Okay, aldehyde A and aldehyde B. Aldehyde A is propanaldehyde and aldehyde B is acetaldehyde. Okay, so there are two different cases for this, and for this particular reaction there are actually four different products that are obtained. So these are the four different products that are obtained for this reaction. Okay, but when you use just one aldehyde or one type of ketone, then you will only form one product. But because there are two different reactants to begin with, there are four different products that you will get. Okay, so in case 1, let's see how you get the four different products. So in case 1, the compound A or the reactant A is actually going to be an enolate, which is actually going to be the nucleophile, and B is going to be the electrophile. Okay, so that's going to be case 1, and they react in two different ways to give the two different products right here. And in under case B, this is going to act as an electrophile, while this is going to act as a nucleophile. Remember, for the nucleophile to be generated, you needed to use a base to abstract the alpha hydrogen to create the enolate ion. So basically the enolate ion is the nucleophile. So here the B is acting as a nucleophile, and A is the electrophile, and they can do this in two different ways, and because of which you can get like two different products. I want you guys, and there is nothing really complicated in this. You just needed to sit down and do the products, and the